I would like to now introduce our second speaker, Dr. Liron Ravner. Following completion of his PhD in 2015 at the Hebrew University of Jerusalem, Dr. Ravner held postdoctoral positions at Tel Aviv University in Israel and then at Networks in the Netherlands. Since 2020, he has been a senior lecturer at the University of Haifa. And in August of this year, Dr. Ravner was awarded the Rothblum Prize for Young Researchers by the Operations Research Society of Israel. Dr. Ravner's research involves mathematical modelling and the analysis of stochastic system, with a particular interest in decision-making in the context of queues and service systems. Today, he's going to present a study of a service system where there's limited information about customer behaviour, but the performance analysis is achieved with some novel estimation techniques. So I'll pass over to you, Liron.
Thank you very much, Nikki, for the introduction and also the invitation to speak in this very unique workshop. And also thanks to the organizers. So today I will talk indeed about work that is joined with Yoshiaki Inu from Osaka University, and also with Michel Manches, who briefly mentioned this work as well in the previous talk. Okay, so the story and motivation here is as follows. Right, when something we often face when we go shopping is we see a long line of people standing before the counter, sometimes a short line. In this photograph, we see a very long line. And then we make a decision. Should we join this queue, or do we go to another shop or try later, and simply leave the system? Sometimes this happens outside of the store. We already see the queue and make this decision. And of course, this happens in many other contexts as well, not just shopping. When we make an appointment to see some specialist, some healthcare specialist, we usually have some online system where we can see when is the next available appointment. When we want to drive somewhere or take the bus somewhere, we can see how long it will take using Google Maps and other applications, or some ride-sharing application. And so in many cases, we have real-time congestion information, be it exact or some estimate, and we make a decision: do we join or not, or balk from the queue? And in many of these examples, before we make this decision, we are invisible to the system. The shop, especially in the second photo here, doesn't know that we were outside in the street looking at the long queue and decided to go home. They're not aware of the potential demand of customers that was missed due to congestion. And this is a case in many systems where the system itself simply does not know the true arrival rate of customers, because some of them left due to the high congestion. So this is a problem we want to approach. And a bit more accurate description of the story in one slide is that there is some service system. Customers arrive with a potential rate lambda. They observe the delay throughout. We'll assume that the exact delay is observed, but this can be also this assumption can be relaxed as well. And if there is some estimate of the delay, not the true and not the accurate waiting time. Customers are heterogeneous in general. That is, patience is some random variable which in the population where every customer that arrives has some patience threshold y, which means if this threshold is above the delay, the expected delay, then they join. And if it is below, they balk. They do not join the queue. And as I said, the system only observes the customers which do join the system. Our objective is to estimate the patience parameter, basically the distribution of y in a parametric setting, and also the potential arrival rate of customers. And we want to do this by using the data only of customers that did join the system. That is the realization of the queuing process, of the effective queuing process, which ignores the balking customers, which are unobserved. Okay, and the talk today I'll first introduce in a bit more detail the topic and the model, and then our specific estimation approach, which is a maximum likelihood approach. Say something about our asymptotic results, and then say how this can be applied and extended, and then conclude. Okay, so generally about statistical inference and queuing theory, I won't say much here because we have a few days of talks really about these topics, and also some overview and survey talks like we had like Michel's talk before and Azam's talk later this week. But I'll just mention some things which are important to this specific work. Is that statistical inference in a queuing setting is not is quite different from the classical statistical problems that well, you learn in Introduction to Statistics courses, where you have some IID observations of a population or a randomized experiment where you take samples from somehow a controlled population. And because queues are generally are dynamic systems where with elaborate dependence between events, right? Between arrivals and departures and waiting times, all of these things are linked together in an elaborate manner depending on the model, and typically time-dependent or transient expressions for things like likelihoods and moments are not available. They are intractable. We do know a lot about stationary steady-state distributions of queues, and we can use that for estimation purposes, and that has been done a lot. I wrote here one example, but of course there are many more. In the context of patience, well, in many systems, you do have some observation of still indirect or censored observation of patients by when you observe abandonment, say in call centers, when the call center knows a customer joined and after some time or even immediately hung up because the wait is too long due to some delay message, or just because they have been waiting and for too long and decide to renege from the system. And of course, there is a lot of work about estimating the patient's distribution parameters or other associated properties using this kind of information. And here I mentioned a few of these papers, but there is a wide literature about this, but that's a bit of a different problem. In our setting, we do not observe anything about the customers who balk. They don't join and abandon. They are just invisible. Okay, and generally speaking, I think in most of the statistical works, statistical oriented research on queuing, you need to use kind of ad hoc analysis to take the system at hand and say something about its dynamics, and from that come up with estimators and studies of performance of the estimators. Okay, and this is basically what we do here for our system. Okay, so the model we assume is an MGS plus H theta Q. which means the following. Inter-arrival times are IID exponential, that is arrival according to a Poisson process with rate lambda. Customers have IID job sizes, denote them by BI, and they are distributed according to some distribution function G, with no assumption made about the form of G. Customers also have IID patience thresholds. We denote these by YI, and they have some distribution H, and we denote H theta because we assume that H theta has some parametric form. Okay, so there is a finite collection of parameters that defines H. Okay, so there are, of course, many examples. Could be exponential, uniform, mixture of exponentials, deterministic patience. Many examples fall into this category. And there are S identical servers that just serve first come on a first come first served basis. Okay, so the key performance indicator that will be important for us in the estimation in constructing the estimator is the so-called virtual waiting time of customers at time t. This is a process we need to first understand how it evolves. And when I say virtual waiting time at time t, I mean if I take the system and stop it at time t and send in a new customer, how long would they wait until their service commences? Okay, so and it's called virtual because customer did not necessarily join at every time t. It's not at specific. It's not only at arrival moments, which may be different from just the distribution at any time t. Okay, this is also related to workload, but as we will see, there is a distinction to be made here. And the queue dynamics are as follows. Customer I arrives at time t, and she observes a virtual waiting time Vt, and I use here Vt minus to denote a limit from the left. That is to emphasize that this waiting time is before she joins or makes a decision whether or not to join. This is simply the waiting time she will experience. And it might change due to her decision. And now she has her individual patience threshold, Yi. If it is above the current waiting time, she joins the queue. And then this virtual waiting time jumps by some random amount. We denoted here by Xi. And which means that if some customer arrives, some new customer will arrive immediately after her, they will experience perhaps more a longer waiting time due to the fact that she joined. But this depends on the exact system state, and I'll say more about this jump in a second. Otherwise, the case where the patience threshold is below the virtual waiting time, she balks and nothing happens, right? The virtual waiting time continues to evolve. Vt equals its limit from the left, and nothing happens. There is no jump, and this is also an invisible event for the statistician wanting to estimate the properties of Y here. Okay, and work is processed at the unit rate, or in other words, that we are always speaking in terms of everything is in units of time, basically here. And when we're looking at this virtual waiting time or workload process, right? For the single server case, there is a simple sample path representation of this process. V0 is some initial workload. So the virtual waiting time at time t is basically the effective amount of work that has joined, all the service times that have joined until time t, minus all the work that has been processed. And work is being processed as long as the queue is not idle, as long as the queue is not empty, as long as there are customers, they are present, they are being served, and so you can write a simple representation of this of the virtual waiting time, and it's easier to grasp, I think, using a figure. Here we see the evolution of the process for deterministic patience example. That is, you see there is a data here. All customers have the same patience threshold, which equals theta. And then they simply join if the waiting time is below it and balk otherwise. So we see here at T1, there is a first arrival. Of course, there is no waiting time yet. This is the first customer in the busy period, and then they join. And the jump is simply, the jump in the waiting time is simply given by the service requirement of the first customer. After some time, work is being processed, and then another T2 units of time, another exponential arrival time, a new customer joins. Still, the waiting time is below theta, so they join. But now they have a bigger service requirement, and the virtual waiting time jumps up until this level, which is higher than theta. And and now what will happen is that new customers joining while the waiting time is too high, the congestion is above theta, then no customers will join. For example, here after another T3 units of time, there was a new arrival, but the delay is too long. It's above the patience threshold, and they balk, and nothing happens basically. Okay, so this event is invisible, and then once it goes below theta again and continues to decrease the virtual waiting time, the next customer will already join again, and then it jumps up, and so on. Okay, so we have this kind of on-off dynamics of arrival, which depend on the waiting time process. So this was for a single server. Generally, for a multi-service system, the representation is a bit more elaborate. You have this. You still have a formula, which is a function of all the primitives of the arrivals and service requirements. I won't go into detail here, but it basically, you have to at each point of time keep in track of how long, how many customers are in the queue, and how many servers are busy, and how long are the residual service times of the customers in service. The waiting time process here is no longer a Markov process. In fact, if you want to look at an underlying Markov process, you have to all the time keep track of residual service times, because if a customer with a short job may enter the system, go into an idle server, and leave before another customer who was a long job who arrived before them. So the dynamics are more elaborate here. But still, you can construct all these this process from the primitives or from the data, if you will. Okay, and now the jump times of the virtual waiting time are determined by the residual service times. Okay, so again, a diagram to illustrate what's happening here. So again, we have this kind of, it's similar to, it's no longer MG1, but now we have an MGS process. We still have this saw diagram, but now we see the green markers are our arrivals, and we see first arrival does nothing to the virtual waiting time. Sorry, in this example, there are two servers. So first arrival means that there is still an idle server, and so the virtual waiting time remains 0. But when a second customer arrives here, then there will be a jump in the virtual waiting time, because both servers are busy. But the size of the jump depends on, will be the minimum of the service requirement of the new customer and the residual service time of the first customer. Okay, so it's more elaborate. It's just not just the job sizes. And then it will decrease, and there will be here another arrival and another jump, which is now a function of both residual service times and the new job size. Okay, so this is how you can reconstruct this process again. And once in a while you'll have departures and so on, and this is how this process evolves. Okay, so this is the virtual waiting time for an MGS system. And here, this is not even specific for a specific patient's threshold. It doesn't matter how they make the decision, but the point is to show how the waiting time evolves. Okay. Now I want to talk a bit more about the effective arrival process. So we said that potential arrivals are IID exponential, but of course effective inter-arrival times are no longer exponential. In fact, they're not independent, and they're not identically distributed in general, because an arrival that occurred now means effective arrival that occurred now means that first it means two things. Waiting time was below the threshold of this customer, but it also means something new was added to the virtual waiting time. There was some jump in the first virtual waiting time, and so the next arrival time until the next arrival obviously depends on this event. Again, we can construct this. We can construct the effective inter-arrival times given the past given the primitive potential inter-arrival times and there's the service requirements by constructing the virtual waiting time process. So everything here can be defined and computed, but it's a bit more elaborate. And this is just a diagram to show the stationary effective inter-arrival time distribution. So the black smooth line here is the potential exponential arrival times, and the red and blue functions here are two examples. One is red is deterministic patients, and blue is exponential patients. And for both of them, we see that they are very different from exponential. Of course, they have they decrease slower because now there will be arrivals, balking arrivals. Some of them are filtered out, so even in the stationary case, when they are identical, the inter-arrival times are identically distributed, they are still dependent, and they have this form which is very different from exponential. And this is what we basically want to reconstruct, to use these effective inter-arrival times as a tool for our estimation. Okay, and we make some assumptions about the queue. They are very mild technical assumptions. One is that customers have finite service requirements in expectation, and the second says that the potential rate, which is so-called rho, the lambda time, the arrival rate times the service requirement, when you multiply it by the limit of the tail distribution of patient, it's smaller than 1, which means that either rho itself is smaller than 1, or that you don't have any customers with infinite patients. Okay, so this basically means that this will ensure stability, and for most behavioral models, this makes perfect sense, especially the second part, because if you assume that customers are sensitive to delay and there is some increasing cost to waiting, then as the waiting time grows, you expect that customers will stop arriving. And then as long as this happens, this means that the stationary distribution exists for the waiting time, for the virtual waiting time process. However, there is no explicit expression for the stationary distribution. For the single server case, you have a nice integral equation that represents the density of the workload distribution, and also there are some results also for MGS systems, but the dynamics make these stationary distributions quite elaborate. But for what's important for us is that the stationary distribution exists, and it exists almost in all cases, because the nice thing about impatient customers is that they push the workload down, and it sort of pushes the system always to stability. So you don't need to worry about stability. You can proceed with estimation. Okay, so that's what we will talk about now. About constructing a likelihood for these level-dependent effective arrival times. So our data is basically a full observation of the queue, which can be summarized as the inter-arrival times, the waiting times, and the jump sizes for a sample of n customers. Okay, and the jump sizes, remember that in the waiting time are in the single server case, that's just the service requirements, but in other cases it's more elaborate than that. But we assume that but if we observe the service requirements themselves and the arrival times, we can also construct these jump sizes by always keeping track of the residual service times. Okay, so if we basically observe the arrival and departure process, we have all these things, and this will be the easiest way for us to describe the data. Okay, we already said that the observations have an elaborate dependence structure, but we can still construct the likelihood of inter-arrival times conditional on the waiting time process. And we do it as follows. First, let's think about the deterministic patience example again, the one where we saw the diagram. We'll look at that again in a moment. So all customers have the patience threshold yi of all customers equals some value theta 0. If waiting time is below or equal to that threshold, they join. Otherwise, they balk. Okay, so if you tell me the waiting time and jump size of the k-1 effective arrival, I know what the distribution of the next inter-arrival time is, because if the virtual waiting time remains below theta 0, it's simply another exponential time. Otherwise, you need to wait some time until the waiting time diminishes below the patience level, and then you need to add a new exponential time. Okay, so again, like we saw before, it's this kind of on-off Poisson arrival process where the on-off is governed by where the virtual waiting time is. When it is above theta, you have no arrivals, and therefore the time until the next arrival will be a sum of exponentials. For example, the third inter-arrival time here that we saw before is a sum of two exponential random variables, because the first one occurred while still above the patience threshold, and the second one occurred already below. So it will be a random sum of exponentials, and we can fully compute this distribution. And in general, you'll have something similar, even when the patience is not deterministic, but just some this distribution H, what you will have is a non-homogeneous in time Poisson arrival process, where the rate at time t, the rate lambda t at time t is a I think this, the notation here is not so good because this could mean here lambda is used as a function, so it should be, so we can change the brackets here to something like this to make sure that this is just a, make it clear that this is just a product. The arrival rate at time t is a potential arrival rate lambda times the probability a customer will join if the virtual waiting time is Vt. And that probability is just the probability that Yi is bigger than Vt, and that's 1 minus h Vt. Okay, or so we can write that as in terms of the tail of the patient's distribution H here. Okay, so we have a kind of level-dependent, non-homogeneous Poisson arrival process. And now we have and like we had before, we can again write the conditional distribution of the kth arrival, conditioning on the past, basically on the previous virtual waiting time, and this will be given by the probability of an event for a non-homogeneous Poisson process. Okay, so we have this conditional likelihood function, which is a function of our data and our unknown parameters, which are lambda and theta, the parameters defining H, and we can then compute an MLE, which is just maximizes the likelihood of the these inter-arrival times that we saw together with the waiting times. Okay, so and this has this, and the likelihood has this explicit representation. So give me H theta, a specific H theta, I can maximize this function. So, and if H is a continuous function, then you have, you'll typically have, you have a nonlinear optimization problem, which is with a solution given by the gradient. And then we make some technical assumptions that we have a stationary system. We already said that doesn't really assume much about the primitives of the model. You have a large enough parameter space. You make some additional regularity conditions about the space of the parametric space of functions H theta. Again, some that they are somehow homogeneous and don't behave too differently in their tail, basically. And also that the log likelihood has a finite expected second moment. Again, these are technical conditions, but they can be verified quite easily for examples. And if everything holds, then what you have is that the estimator converges almost surely to the true value as you increase the sample size, as you observe more customers. And also you have the asymptotic distribution of the estimation error scaled by square root of n. It goes to a normal distribution with a covariance function that can be computed. Okay, and this is somewhat standard tools, but again, but that need to take into account the dependence between observations which basically means that you need to verify some steps specifically for the MGS plus H system and the dynamics of the waiting time. But this can be done. Okay, if patience is deterministic, then something the MLE behaves a bit differently. Actually, it's quite intuitive. The MLE is simply given by the longest waiting time that you observe, right? And if you think about it, if all customers have the same threshold theta 0 and you want to estimate theta 0, you will simply take the highest observed waiting time is your best guess for for theta 0 because you expect it to get closer and closer to theta 0. And indeed it does. Again, also for deterministic patients, you have almost sure convergence to the true value. Now the asymptotic distribution of the estimation error converges quicker at the rate of n to an exponential distribution, and this may or should remind you of estimating the boundary of a uniform distribution, or estimating the boundary of a distribution with a continuous distribution with a finite support. You get these kind of results, but again, you have to use a specific dynamics of the queuing system, and it's interesting that it's the asymptotic exponential distribution is related to the density of the waiting time at the threshold level, and also the probability of loss in the system. Okay, so again, this requires some ad hoc analysis of the system, but you can this can be verified. Okay, and so that basically we have two different cases here. One where you have kind of discrete patience options, like the deterministic case, or continuous distributions for patients, which maybe make more sense in heterogeneous population. Okay, now I don't know if I'm not sure I even said it, but in general we assume that the lambda was known in the last few slides, or I didn't say anything about it. But if we want to estimate lambda as well, it's not a big problem, because the likelihood that we had before is a nice concave function of lambda with an explicit solution for its maximizer, which is written here. Okay, so you need to compute some things here, but basically, if you can estimate theta n, like we did in the previous slides, you can estimate lambda as follows, just by plugging in your estimator for theta, and of course it's a statistic of the data itself, of the waiting times and effective arrival times and jump sizes. Okay, so lambda is has an explicit solution for the MLE. And then consistency and asymptotic normality follow in the from the results for continuous patience distributions. Okay, so there is no additional challenge in jointly estimating theta and lambda. It's basically just adding another parameter to the theta vector, and all results follow, and this can be applied. Okay, so once we have this asymptotic theory, we can first of all, we know that it works, and we have verifiable conditions, and we verified it for various examples. I'll mention first. We looked at exponential patients and constructed confidence intervals. So here you have a numerical example with 5 servers, exponential distributed patients, that is with one parameter, 0.4, determining the patience of customers, potential arrival rate of 1, and gamma distributed service times, and we could compute confidence intervals for a sample of 2,000 customers, the insight we got from this experiment, for example, is that, well, if you look at the estimator of theta at the, and maybe it would have been nicer as a figure than to illustrate it. But what you can observe is that as rho increases, the estimator for theta, for the patience parameter, becomes more accurate. That is, there is more information in a highly loaded system. because you somehow observe more bulk. You don't really observe bulking, but it happens more often, and it turns out that you get better information from a highly loaded system. But for the arrival rate, it looks like it doesn't matter. You have a bit of a reverse effect, but basically you are very accurate regardless. It seems like, the arrival rate estimating the arrival rate is a much smaller problem, and you generally have much smaller variance for the estimation error of lambda. Okay, so this was one example. And another a more general class of parametric distributions is a generalized hyperexponential patients, which is basically a mixture of exponential random variables, but they may have negative weights. Okay, so the alphas here may be negative. That if they are all positives, then it's called just a hyperexponential distribution, but they may also be negative. Of course, what we just saw, the exponential distribution is a special case, but also any mixture of exponential distributions. And what's nice about this class is that any positive continuous distribution can be approximated by a generalized hyperexponential distribution. And so this leads to several examples. Well, first of all, for this class of functions, we can verify all the assumptions we needed for the asymptotic analysis. That means that the MLE is consistent and asymptotically normal. And we also have some expressions for the asymptotic variance, which can be computed. And then you can also construct confidence intervals for more elaborate models. But what's really nice here is that if you don't have an a priori belief about what the exact model is, what the parametric patience distribution should be, you can use a GHE to approximate any continuous patience distribution. And we suggested a simple heuristic that does this by looking at different number of weights for the mixture, and then computing the corresponding MLE for the generalized hyperexponential distribution, and then looking what model has the best information criteria. We use the Akaike information criteria, but generally you can do other things as well, as long as you also somehow penalize for the size of the model. Of course, as you take more and more weights, bigger mixture, you'll get maybe better likelihoods, but you don't want to overfit. Okay, and this performs very well for the models we tested, at least. Okay, so basically we observed that, well, you don't need to search a lot. You can fit with a small number of weights. You can find a really good fit for a misspecified model for where the true patience distribution is continuous but unknown. You can do quite well. There is a drawback here that optimization step seems quite hard for the GHE distribution, but this could also be due to our lack of optimization skills, and so say off-the-shelf optimization algorithms did not perform very well here. We had to tweak some things, but I think this can generally be worked out. And here is one example of a log normal patients where we try to fit different hyperexponential distribution and generalized hyperexponential distributions. And well, the red line here, which is not close to the true distribution, is a simple exponential. But once you take a mixture of two exponentials or three or four, you start getting a really good fit. And if you do the GHE heuristic I outlined, you get a very good fit for the log normal example. And we also we tested the other distributions as well, and you see that this is, as long as the underlying patience distribution is continuous, you can get a very good fit using the GHE model selection. Okay, so and other very special cases can be, the asymptotic conditions can be verified, and we can also extend this method or refine it to situations where the waiting times are not known accurately, but you have some noisy estimator, or you get some noisy estimate of the delay, and in many cases you can apply this as well. Or if customers have discrete queue length information and not the waiting time information, then you can also employ some a similar MLE construction for the effective arrival process. If there is, and then if you can also combine this with some admission policy, say with pricing, if there is some price which then interacts with the patience of customers, and then you may possibly change it over time, and then we believe that this or it can be applied in a naive way, but we haven't studied the performance of such a dynamic problem as well, but we believe it's promising. Or other cases, there are other extensions and refinements that you can look at here. And I think my time is basically up, so I will just summarize quickly. What we saw is that we can estimate the arrival rate and patience distribution for the system with unobserved balking, and we provide variable conditions for asymptotic performance, and we verify these conditions for several examples. We can estimate arbitrary continuous distributions using the generalized-hyperexponential MLE, and we can also widen the scope or the framework to some other assumptions about the system, and still employ a very similar method with very similar performance. Yeah, and I'll wrap up here. Thank you.
Thank you very much, Liron. That was an excellent talk on a really well-described system that was, I guess, had some really good physical interpretations. So I can take questions to Liron through the Q&A function, or if you'd like to raise your hand, you can ask a question with audio. So please send them through. I guess I can kick things off with, you mentioned in your work, Liron, that there's this natural extension building in correlations between service requirements and the patient's level, like having longer service requirements, those people might be a bit more patient. What kind of complexities are you going to run into when you go for the generalized model?
Yeah, so that's a very good comment question, and I think conceptually you won't run into much problems. We did think about this, and it seems it's not, we didn't incorporate it in the paper, but it seems like you should be able to write this in the likelihood function, and that conditional likelihood function, it will just make the expression in the integral corresponding to the non-homogeneous Poisson arrival process a bit more elaborate, and that when it will and it will depend on how exactly they are correlated, the service requirements and the patient's times. But it seems that give me some specific assumptions on how they are correlated, you should be able to still estimate everything that you want. The key is that you can still write this likelihood function of the effective arrival process, and from then on continue. And of course that will raise some technical hurdles in implementation, and maybe in asymptotic analysis you need to verify some more things, but it seems that essentially that the same method should work. It doesn't move you completely outside of this likelihood framework.
Okay, well, that's very encouraging. And I guess it means that what you've presented is really nicely extendable. We've got a hand up from Peter Taylor. So Peter, I've just allowed you to talk, so please go ahead.
Thanks, Nikki. Can you hear me?
We can.
Yes.
Right. So Liron, is there an assumption in your model that the customers can observe the virtual waiting time?
Yes.
So how realistic is that in a real system? I mean, even the pictures you had at the beginning of the queues, you see a long queue and you can have a proxy for the virtual waiting time in the sense there's a lot of customers there, but you don't know exactly what it is, do you?
Yeah, that's correct.
Yeah.
I definitely agree that, I say, maybe in some computing systems you do, and in some cases you do, but in many or most cases you do not know the exact waiting time. And so I said this very briefly, but and we discuss it a bit more in detail in the paper. You can still apply this framework even if you have, say, noisy delay messages, say, not exact waiting time, but some estimator of the waiting time. As long as you need to make some assumptions about the mechanism which creates this estimator. Say that you get the waiting time plus some estimation error, and then you can invert this back to the likelihood function. That's still doable, and we give a couple of examples. So generally you can handle that situation as well. And also we talk about what the second thing you said about the discrete queue length information, which is also common in many systems. And from that information, you can either go back to waiting times when it makes sense, say in a single server and exponential service times, right? It's quite natural to go from queue length to expected waiting time. In other cases, maybe there is a slightly different way to adapt the likelihood function, but still you can construct it as a somehow discrete level dependent non-homogeneous Poisson process, which has different rates at different levels of the queue, and still in a quite similar manner you can estimate everything. Okay.
Thanks.
Short answer is that yes, I believe you can make more realistic assumptions and still use the core of the framework. Yeah.
Okay. If anyone else would like to put their hands up, please go ahead. In the meantime, Liron, how possible would be to take your model and some of your methodology and look at a kind of non-stationary system or something that's in a random environment? Is that possible?
That's also a very good question, and indeed something we thought about, especially when you look at data and it's immediately obvious that arrivals are not stationary in many settings. So yes, the answer is, again, I believe it can be incorporated. Again, it will make the likelihood function of the effective arrival process more elaborate. You'll have here another dimension of both wait congestion level and the time itself. Or some parameter of a random environment, which you need to incorporate. But essentially, I think it can work. And not a few weeks ago, a PhD student started working on making this on this extension of allowing non-stationary arrivals with some underlying time-dependent structure. And student Michel and I are co-supervising, and hopefully we'll have also some results for that model as well. But we are quite optimistic that indeed that can be done. Okay,
great. We've got one hand up for our last question, so I'll just transfer the audio. Should be able to speak.
Hello, sir.
Hi, we can hear you.
Yeah,
yes, sir.
I hear you.
Yeah, actually, my question is that is this system is fully unobservable or partial observable?
You mean for the customers?
Yes.
That's also a good question. So indeed, we assume here fully, at least in the base model, a fully observable system where customers arrive and know their exact waiting time. But also, as I said to Peter before, you can relax this into some partially observable case where you observe just the queue length or some estimator, or if the waiting time is above some threshold or not, or you can also consider a bit more elaborate information structures.
Okay. Thank you, sir. Thank you.
Okay, great. Well, thank you, Liron, for an excellent talk. But we should take a break for a few minutes and return with the final speaker of the session. So thanks again, Liron, for an excellent talk.
Thanks.